Hello everyone, this is Calvin, and today let's talk about audio recognition model with Python and TensorFlow. And the example here is to find the running tap water sound in the audio file. So we're going to find the timestamp of running tap water sound in the audio file. Okay, so I'll go through the context and then the solution overview is like the structure on how the solution works before we go through the detail of the solution. So I'm going to show you the dataset, the code, and also the result of running the test to the model. And of course, there's always been a learning and improvement point. And we will also go through that one, right? And let's go to the file. Okay, so this is the context. So as we mentioned, this is to determine the timestamp of a tap water sound in the audio file. And actually, this is a hackathon in my internal company, and it will be started in a few days. However, before the real hackathon, they always told us the sneak peek of it, right? And I think the sneak peek was very clear. So that's why rather than waiting for another few days, I just started exploring this, just because I love this. So my motivation is for the learning and networking. I mean, hopefully someone in the, I mean, no, I mean, it would be fun. It would be funny if someone found this video. I mean, someone from us, a colleague found this video, and I mean, if someone found this, yes, please say hi to me in the Teams. Yeah, hopefully this is also a good portfolio for me to move role to the data job. That's just my motivation. And then, and anyway, this real fun to do this stuff. Okay. And why we want to find the tap water sound is because and the story, I mean, just the story is because we would like to determine how much water is consumed during the use of our company product, and this will relate to the sustainability. Okay. And then the challenge itself will have the sample data set of audio file in various format, maybe because it's not started yet, but I'm assuming it will be in a different format because it will be recorded from a different type of devices, and then different bit rate for sure, and different channel for sure. And yep, and then and this is a lengthy audio file, right? And it will be also given CSV files for each of the audio files, detailing the start and stop or the timestamp of the tap water sound. So like this row, for example, for audio 1 in from 0 to 0.5, there is no water. But from 0.5 to 1, there is water, something like that. And this is explaining this audio file basically. Okay, and then the test data set would be similar, so it will be audio file, various format, bitrate, channel, same, and the expected output is basically this thing. So from this test audio file, we should generate this kind of CSV file basically. Okay, And then, right. Now it was the context, and we'll just go through the solution overview. And I put a note in the first here that I know the solution below have a lot of improvement points for sure. And the important thing for me is I'm happy that the concept is proven work, because you know, this gives me a good chance to learn all about this, and this is my first time building a model with the audio file. I mean the model to predict audio file. Okay, and I also put that I got the idea from a TensorFlow tutorial, and anyone can just follow the link or Google audio classification TensorFlow. And my approach is I would like to tailor it to match the challenge above. So because although this tutorial works, but it is not in the same format as our challenge exactly. Okay, and the working solution would need sample dataset and label in this format. So mention just for example, so the first label would be water, and it means the sample of the tap water running sound, and everything should be in the same amount of second in the length, just putting a 0.5, and every one should be WAV file and should be in the same sampling rates and should be in the one channel. And the second label should be a non-water basically, but it's just a sample of a non-water sound, like anything else besides the tap water running sound. The test dataset should also be in the same format as this one. So if we frame it like this, then it will become a binary classification model. It's like positive if there is water and negative if there is non-water, basically. And then, oh yeah, just put a note here that the model, of course, should be safe, so it can be run without redoing all of the model learning, of course. And then this section is I'm putting a note here that the data set provided in the challenge is different, definitely. So that's why we need to tailor it. So preprocessing and post-processing should be needed. And this bullet point is I'm just reiterating the different of the data set provided in the challenge versus the working solution. So as mentioned before, the dataset provided in the hackathon challenge is in this format. So one audio file with the details of the timestamp of when there is water or non-water, and then the audio format maybe varies, maybe not only WAV but also another format and different sampling rate, sometimes 16K or another, or different channels, sometimes one, sometimes two. So basically the pre-processing is we should process this, so it will be in the format that the working solution can work with. Okay, and we'll go to the pre-processing right now. So, all right. So the idea of pre-processing is we go through each sample dataset and split it to water and non-water. Okay, because we already know the timestamp from the CSV file, and let's see. Oh yeah. So after we split it into the water and the non-water, we still need to split it again by the window that we choose, which is X. So let's say this example from here to here. So in this example, the audio one is what is a non-water from 0 to 2.4 seconds, just for example. But see here that we still need to split it with 0.5 seconds, because we want to have the same X or the same window for learning the model basically. And then similarly for the rest of the example. So for example, for the audio one, it is water from timestamp 2.4 until the rest, and we still need to also do the same, that we should split it again and again basically. And I'm sorry, this is wrong. This is wrong number. This should be this one. I just noticed. Right, that makes more sense, right? Save. And then, oh yeah, the name does not really matter in the model, but basically we split it. All of the non-water event should be split in the 0.5, and the water event split into 0.5, something like that. Then for the why I say the name does not really matter here is because for the test data set, the name will matter actually, a bit matter. Okay, so now for the test data set, the first note here is we should create a table to document the original name and save that for later reference. I will go through this why in the below. And then similarly, we should also split the set into X second. And this time, of course, we do not know yet whether it is water or non-water, right? So we just need to split it like this. So let's say the audio file name is test1 with a length of 1.71 seconds. Then we should split like test1 from 0 to 0.5, test1 from 0.5 to 1, and etc. until the final length of the test1 audio file. Then I think intuitively the table would look like this. So the name is test1, and then this is the split name would be just give it a different name just to make it different files, but practically they are all part of the test1. And this is the timestamp just for the nodes here. Okay, and of course we don't know if this is a water or a non-water yet. This is just a pre-processing. Okay, and then oh yeah, and then another things, and I put as well the post-processing here. So we are the explanation about pre-processing is done from that point above, and for the post-processing is basically you can imagine the testing result, right? So from this one, then we will run this through the model, and then the model will predict if it is water or non-water like this. And then the idea here, and I know this is a bit non-straightforward, but as I mentioned, this is one of the improvement points that will be covered later. However, we would like to combine this table and this table, combine this, so it would go through this table, basically. I think got the idea, right? So the original table is only containing the name and the timestamp, and the second table is containing only the prediction of each new name. So this is the key, actually, like this, and the rest of it should be combined into one. And this table will be same with the with have the same column with the expected table as we have in the beginning, right? File start stop water, and this is also file start stop water, right? And then just one bit more of it is because we split it one by one blindly like this, then we should just need to combine. If there is any same event like this, then let's just combine it into one event like this, right? All right, we have gone through the context and solution overview, and let's now go through the solution and starting to see my own recorded dataset. And why am I recording my own dataset is because, as I mentioned, the hackathon challenge itself is not yet starting, right? So there is no formal dataset from them. And so I just simply recorded myself, go through my tab in my apartment to the sink, I mean, and just recorded it. And hold on. Let me repeat. Okay. Okay. Hello. Okay. All right. So we have gone through the context and the solution overview, and now let's go to the detail of the solution by looking first at my own recorded dataset. And why am I recording my own? Is because, as I mentioned, the hackathon itself is not yet starting, so I don't have the dataset from them. And then I just simply recorded it myself by going to my sink and record it using Windows PC. And this is the result. So we have this water sound sample, and a non-water sound sample is for the sample dataset. And this test data, water and non-water, is the test dataset. So water sound sample is a sound of running tap water with some noises here and there randomly. Let's hear it quickly. Yep. So as you can hear, it's a sound of running water, and I put my voice here, and later on, I think I also put some random noise like like clapping sound or some hitting some noise like that. And non-water sound sample is sample on there is no water here. So and this is sound without any water. Something happening there. Yeah, something like that. So human voice and combined with the other random noises, however, without any water sound. And the test data water and non-water is for the test data, and this is consists of water sound as a non-water sound randomly and intermittently. So I just turning on and off the sink intermittently. I mean the tap water intermittently.
Okay, recording test dataset. There's some water. I'm stopping the water. It's walking around. Stop it. Turn stop. Stop. And
Yeah, something like that. So sometimes I turn the tap water on, sometimes turn it off randomly, and I put some human voice, sometimes I put some random noise and turn on, off, like that. Okay, so we have seen the recorded dataset by myself, and now let's see the code and sample of the result. So I just make it like this. Sorry, 1, 2, 3. So the first code is for pre-processing, second is for model and processing, and the third one is for post-processing. I didn't think much when when putting all of this stuff. It could even be at the one file if anyone wants, but I just think this is easier for me to categorize. So the first one for pre-processing is first is pre-processing all of the file format into the WAV file, and make the channel into one channel only, and make the sample rate into 16,000. And I will not go through each of the code, but I will just let you know the idea of it, and I kind of combine my experiment here with the real data. So the first point is for me just playing around with the how to get the sample rate, how to get the channels, and how to change the sample rate into from this into this, and how to change the channel from 1 into 2, although we will do the opposite actually. And then here I also put a note, and first function is to change everything to WAV, and then the next one is to change all of the WAV file into the correct channel and frame rate or bit rate. And this is just an example. So I took all of the file from the directory of the folder where I put all of the file in this folder, and then it got this data. So some is to M4A, some is WAV, and etc. And then the first method or function is to take all non-WAV file from the directory, so which is this one, and change everything to the WAV basically. So this one is to take the file names, and this one is to change it. And if we can see, let me see if I can. I think I don't need to show the folder, but in the folder that all of this data is changed to the there is a new file actually. There is a new file having the WAV here, like just like this example, which is oh no, so I didn't recheck it here, but anyway, even though I didn't recheck, now you can see that from the M4A we can find the WAV file now. Okay, and then after that, now since we already got the WAV file, then let's change it to the correct channel and frame rate. And now we are getting all of the WAV file, and from the each of the WAV file we change everyone to the one channel only, and change everything to the 16,000. And then after that, and this time I make a double check. So and by the way, I put as well the pre-processed here in the new file name. So I know that this new files is the um, is a new file that I created basically. So now where is that? Oh yeah, now here is I put this is the pre-processed WAV file, and I mentioned here that I double check the WAV file to check if they have the one channel and the 16,000 frame rate basically, and it turns out that it is true. So all right, so now from this point that everything is already in the WAV file and already in the one channel only and already in the 16,000 frame rate. And now after that, then the next point is to split them, because as we remember from the for each audio file, we will also get the sample data set of the timestamp of where it is water and where it is non-water, right? So I just put my own timestamp here for the testing, and yeah, basically the first part is to read all of the CSV files and to pandas data frame, and then after that, yes, it's like, because we choose 0.5, so I'm gonna use a 0.5 here and to split it. And this, from this point, is just my experimentation. And then let's see, where is that? Yeah, just like this one. So this is how we've split it. So from, let's say if the file is from 0 to 0.7, then we should split it like 0 to 0.5 and then 0.5 to 0.7, something like that. And then we will just go through the final result. So this is the final result. So finally, from the CSV file, we will process the, let's say this one is the pre-processed non-water sound sample. This is just a name of the WAV file. So the start is from 0 to the 21 seconds. And it have this one for everything is a non-water here, because this is non-water sound sample. So everything is a non-water, and see it is divided by 0.5 seconds from start to the end. And the second file is name is pre-processed water sound sample, and from 0 to 27, and everything is water here, because this is just a water sound sample. I intentionally make it like this so it is easier for me to split. Okay. Now from here we got everything is already split basically. And then after that, the above is only for the sample dataset, and we will do something similar to the test dataset. And this one is easier because we don't have to read any CSV file. We just blindly split everything to 0.5. So the concept is the same. It's only that, yep, It's only that and this is how it works in the in my experimentation. So I just put the I just generate uh the the number to the split, basically. Just I mean from the minimum point to the maximum point, and split everything by 0.5 and put them together and zip them together, basically. And then just use it to in the for loop. And this is the example, and this is the real thing. So it is pretty much similar, but basically we will go through each of the audio file in the directory, and then basically go through each of them, and then take a look at what is the maximum length and process it, basically. And it goes like this is the, for example, for this file, then it will go from 0 to 35, and you know, split it by 0.5 seconds, basically. That's it. And finally, put it back to the data frame and put them into a CSV file, basically. That's it for the pre-processing. We have gone through the pre-processing, and now let's go through the model creation. And as I mentioned before, this is taken directly from TensorFlow, what do you call it, tutorial in their website. So almost 90% of the code is coming from that, and I just did a simple tailoring, basically. So let's not go through line by line, but rather let's see the interesting part to our application in the tap water sound. Okay, so all of them. Okay, let's go through it. So most of the beginning is only for getting the dataset into the model and split it into train and validation dataset, and then make it more fit with the model. I mean, make it more suitable with the model that we want to create, and then stuff like that. And this is the first example that is nice to see. We can see some of the time domain visualization of the water and the non-water. It looks, I mean, we cannot really see anything here, but here we will go through the spectrogram of it, and we will see later. But from my human eyes, I can see that if this is water, then it looks like the frequency is more broad, I would say. It's like it has from the lower frequency to the higher frequency. I think that's also the reason some people mention that a water tap sound is actually a white noise, which is consisting of all frequencies. And we can see here a little bit more that the water sound have broader frequencies, same, right? So it has it it's relatively more more green color here in the above part compared with the non-water. There is not so much there, and it's like almost full of color, basically, if you can see. And same goes like, yeah, like this one, right? So not so much color above, I mean green color. Okay, and then and the next one is the modeling, and this model is I'm just taking for the current best approach to detect the sound, and I didn't change much on this one. So this is the recommended model, and I just use it. And next is the model training, and then this is the accuracy of the model, not so bad. And this is the confusion matrix of it. Seems it can correctly classify. And let's see them. So by this point, we have already made a model, and now the next point is we will just like to predict each of the files, basically, which is going through each of the test dataset and run it. And yeah, it's simply just call the model and pass through each of the sample file. And let me just show you. So this is the final one. So finally, this is the, I mean, this is the split file. So, and like file 1, 2, 3, 4, 5, whatever. And this is the prediction. This is non-water, this is water, and etc. And everything is put to the CSV. Okay. Now we go to the final step, which is the pre-processing. So in a simple term, so this will take the data from the CSV files that we've created. The first one is the original naming, I call it. So this is just the file name. This is the split file name, and this is a start timing. This is a stop timing, and this is the prediction result that we just got from the model creation, which is the split file name and the prediction. So you can see that basically we want to combine this one and this one with the split as the key. Basically, we want to join them. Okay, and this is the finally the joined result from like this. This is the original file name, and this is just start stop timing, and this is the prediction. But we can see there is same one like 0, 0, 0, 0, 0. So actually this is a continuous time, right? 0 to 0 0.5, 0 0.5 to 1 is a continuous time. So the next one is the, where is that? Oh yeah, this is just my experimentation on how to do it. And where is that? Oh yeah, I put a category here, and I need to tell you guys, I don't know what is the more Pythonic way to do it, and this is actually one of the improvement points. So simply I just put a category here for each of this. Like this is category 1 because this is one segment, category 2 for the second segment, and etc. And then the next one is I group them by the category, and like find the minimum start time and maximum stop time for each category. So I got all of this. I don't know, maybe you guys know a better way, but I've been thinking about this, and I think this is the, I don't think this is the best way to do it, but it works. All right, now we get it. So this is the result, and we can double check actually from the sound record.
Okay, recording test dataset.
So see, this is at the third second, right? You can hear a water sound and here, right? Until around 5.
There's some water.
It's, I don't remember if this is a sound on a water or not, but the model predict between 5.5 to 6 there is no water, but I think I can still see a faint, I can still hear faintly a bit of sound, so maybe the model didn't predict correctly on this one. But let's see the next one. Yep, you can see from 5 sorry, from 6 to 9, there is water and it's correctly there, right? Let's see, and model predict from 9.5 to 18, there will be no water.
I'm stopping the water, swapping around, creating some noise. Let's turn the water.
See, it's correctly predict that starting from 18, there will be water again.
Stop it.
And this is not exactly 20, but maybe it should be 19.5, but it's kind of okay. And let's see, it should start again in half second.
Turn the water again.
And see, from this point is intermittently, because when I record this, I also intentionally make it like on off like that. And let's see, now is 23 here, so should be nothing until 1 second, and then like every 1 or 2 seconds.
Stop it. Turn stop. Stop.
Yeah, we are now at the 30, and I think it nicely captured the on off. I think it's nicely captured that point. Finish. Yep, that's all, I think, and I'm honestly quite happy. This is not the perfect, this is not the best model, but I'm happy because I can learn some of the stuff, and the result is, I would say, is not so bad for a first time model, but definitely it can be improved more, which I put here. And this is some of the key learning that I put. Now we go to the ending of the session, which is the key learning and improvement point. And first is I use PyDub to work with the audio. It's powerful and wonderful. Although I mean, once I know how to use it, it is good. But it just took me some time to start it, because there is this file that needs to be on the same folder as the PyDub. It's the one thing. And secondly is yeah, as I mentioned, I learned a lot in doing the deep learning with the audio, because I've never done this before. I took some extra courses in machine learning and deep learning and artificial intelligence. However, the courses only cover a picture of, I mean, modeling the picture or image, basically. So I'm happy I can have a chance to work with audio. And then for the improvement point, the first one is, as I mentioned before, I pre-process the test data and split it into separate files. But probably rather than doing this, one can also do it while processing itself. So doing the splitting together with analyzing it doesn't have to be here. But this one, what I did is for, as I mentioned, proof of concept, and it is easier to debug if there is something wrong. And second point is, oh yeah, the window chosen for analyzing is 0.5, but as we can see from the result here, so the precision is basically 0.5 seconds, right? So it doesn't really detect smaller than 0.5. I think we could experiment for 0.2 or 0.3, maybe. We need to try. But when I tried it the first time, I do not want to use too small, because it may prone to overfit. Even another example, in the internet, people show like 1 second, so 0.5 second is even smaller than another sample in the internet, basically. And then the third point is, and I mentioned a bit during explaining the code, this one. So to change this data frame into this data frame, I don't know yet what is the easy, simple way to do this transformation in the more Pythonic way. Yeah, mine putting a bit of manual effort here and there, and probably there is a better way. And the last point is I also mentioned when I explained the code, so there might be a better deep learning model. This one, where is that? This one. So this network is I'm just using the example, and they probably we can still play around on the on the number of layer, number of nodes, stuff like that, or another layer of convolutional neural network and stuff like that. But I think this is something that can be explored further to make a better model. I think that's it. It's been a bit long video actually. So thank you very much. And yep, that's it then.